Imagine waking up in a world where every decision is a shot in the dark. Businesses guess what their customers want, doctors make treatment plans based on intuition, and weather forecasts are little more than educated guesses. Fortunately, we don't live in that world. Instead, we're surrounded by data. Oceans of numbers generated every second from our phones, our purchases, even our daily routines. But raw data alone is meaningless. Enter data science and statistics, the twin engines powering our ability to turn chaos into clarity. Whether you realize it or not, these fields shape the way we live, work, play. From the moment you get a personalized movie recommendation to the instant your GPS recalculates your route, data science is quietly working behind the scenes, making sense of the numbers. But how does this all work? What transforms a jumble of data points into actionable insights? The answer lies in statistics, the foundation of all data-driven discovery. In this video, we'll embark on a journey to demystify statistics, exploring how it underpins the fascinating world of data science. Let's unlock the secret language of numbers together. Before we dive deeper, let's clarify exactly what statistics does in the context of data science. Think of statistics as the toolkit that empowers data scientists. Interpret, analyze, make sense of the vast rivers of information flowing through our digital world. At its core, statistics provides the methods to collect data, responsibly organize it, efficiently summarize it in a way that reveals hidden patterns. But that's just the beginning. Statistics helps us spot trends, measure uncertainty, make predictions even when faced with incomplete or noisy data. It allows us to ask meaningful questions, test our ideas, avoid the pitfalls of jumping to the wrong conclusions. In data science, every algorithm, every model, every visualization is grounded in statistical thinking. Whether it's understanding customer behavior, optimizing supply chains, detecting fraud, statistics is the silent force guiding our decisions. By applying statistical principles, data scientists transform raw data into reliable knowledge, driving innovation, solving real-world problems. In the next chapters, we'll see how these fundamental concepts come to life, and why mastering statistics is essential for anyone who wants to unlock the true power of data. Now that we understand the role statistics plays in data science, let's explore how it helps us make sense of the overwhelming amount of data we encounter every day. Imagine standing in front of an enormous library filled with millions of books, each book representing a single data point. On their own, these books don't tell you much, but with the right tools, you can quickly find patterns, spot outliers, identify important trends. This is where statistics shines. It acts like a librarian, organizing and summarizing massive collections of information so we can easily understand what's going on. For example, with just a few statistical measures, we can determine the most common value in a dataset, see how much the data varies, find out if two sets of numbers are related. Statistics isn't just about crunching numbers. It's about transforming confusion into clarity. By applying statistical techniques, data scientists can clean up messy data, highlight the most important details, filter out the noise. This process makes it possible to turn raw, unstructured information into insights we can act on. Whether you're analyzing customer reviews, scientific measurements, social media trends, statistics provides the framework for making sense of it all. In the next scenes, we'll see how statistical concepts like central tendency, dispersion, probability give us the power to truly understand the stories hidden within our data. Statistics isn't just for scientists or data analysts. It's woven into the fabric of our daily lives, often in ways we don't even notice. Every time you check the weather forecast, read about election polls, see sports averages on TV, you're witnessing statistics in action. Think about your morning routine. When you decide what to wear based on the chance of rain, you're relying on statistical models meteorologists use to predict weather patterns. When you hear that 8 out of 10 dentists recommend a certain toothpaste, that's a result of statistical surveys and sampling. Even your favorite apps use statistics behind the scenes. Music streaming services suggest new songs based on listening habits of thousands of users, finding patterns using statistical analysis. When you shop online and see most popular, top-rated products, those rankings are built on statistical summaries of user ratings and purchases. Statistics also plays a crucial role in public health. During a flu season, health organizations track infection rates, use statistical tools to predict outbreaks, and guide vaccination campaigns. In sports, coaches use player statistics to make strategic decisions and improve team performance. No matter where you look, statistics helps us make smarter choices, spot trends, and understand the world a little better every single day. In the next scene, let's dive deeper into how statistics empowers data scientists to unlock the true power hidden within data. Now that we've seen how statistics shapes our everyday lives, let's take a closer look at its two main branches. Descriptive inferential statistics. Imagine you've just finished a big survey, collecting data from hundreds of people about their favorite ice cream flavors. What do you do with all those responses? This is where descriptive statistics steps in. Its job is to organize, summarize, and present your data in a way that's easy to understand. Think of charts, graphs, averages, percentages. Descriptive statistics helps you answer questions like, what is the most popular flavor? What is the average age of ice cream lovers in this survey? But what if you want to go beyond your survey group? Maybe you want to predict what the whole city prefers, not just your sample. This is where inferential statistics comes into play. By analyzing the data you have, inferential statistics allows you to make educated guesses or inferences about a larger population. It helps answer bigger questions like, based on this sample, can we predict which flavor will be the city's top pick? How confident can we be in these predictions? So in short, descriptive statistics describes what's in front of you. Inferential statistics uses what you have to make predictions about what you don't. Both branches work together, turning raw data into valuable insights. Whether you're running a business, conducting scientific research, or just trying to figure out what to serve at your next party, let's see descriptive statistics in action. Imagine you're a manager at a coffee shop chain, and you've just gathered a week's worth of sales data from all your locations. At first glance, it's just a long list of numbers. Cups, sold, revenue, customer visits. But with descriptive statistics, you can quickly turn this raw data into valuable insights. First, you calculate the average number of coffees sold per day. This helps you understand your typical daily sales. Next, you look at the range. Busiest day, slowest day. This gives you a sense of how much sales can fluctuate. You might even use a simple bar chart to visualize which days of the week are most popular for coffee runs. You can also break down your data by product. Which drink is the best seller? What percentage of total sales comes from pastries versus beverages? Descriptive statistics organizes all of this information into easy-to-read tables and graphs, making it simple to spot patterns. In just a few steps, you've gone from a confusing spreadsheet to a clear picture of your business performance. This is the power of descriptive statistics, turning overwhelming data into straightforward, actionable knowledge. Now that you've seen how descriptive statistics help us organize and summarize data, let's take things a step further with inferential statistics. Imagine you're still managing that coffee shop chain, but this time you want to launch a new seasonal drink. Instead of surveying every single customer across all your locations, you decide to ask just a small group for their opinions and purchase habits. Here's where inferential statistics comes in. Inferential statistics allows you to take the information from this small sample and make educated guesses about your entire customer base. It's like taking a sneak peek at a few puzzle pieces and predicting what the whole picture might look like. With tools like confidence intervals and hypothesis tests, you can estimate how popular your new drink will be, or determine if a marketing campaign truly increased your sales. Instead of just describing what's happened, you're now predicting and making decisions about the future. By using inferential statistics, you're not just reacting to data, you're using it to guide your next move. This is how data scientists turn a handful of information into insights that drive big decisions, helping businesses innovate and grow. In the next scene, we'll see how the power of statistics transforms raw numbers into real-world impact. Have you ever wondered how Netflix knows exactly which show you'll binge-watch next? Or how your favorite food delivery app predicts your delivery time with surprising accuracy? The magic behind these everyday miracles is not really magic at all. It is data science. At the very core of data science, like a secret language that everything is built upon, is the powerful field of statistics. For anyone aspiring to become a data scientist, or even just understand the modern world, ignoring statistics is like trying to read a book without knowing the alphabet. It is the fundamental grammar that allows us to understand the stories that numbers are trying to tell us. Without it, data is just a chaotic jumble of digits. Think of it this way. You have a massive spreadsheet with thousands of customer purchases. On its own, it's just a wall of text and numbers. It's overwhelming and doesn't tell you much. But with statistics, you can start asking intelligent questions. What is the average amount a customer spends? What is the most frequently purchased item? Are people who buy product A also likely to buy product B? Suddenly, that messy spreadsheet transforms into a treasure map, leading you to valuable insights that can help a business grow, improve customer satisfaction, make smarter decisions for the future. Statistics is the tool that turns raw, unprocessed data into actionable intelligence. This is not just about business. Statistics is everywhere, shaping our lives in subtle but significant ways. When you read a news report about a political poll, that's statistics telling you about public opinion. When doctors evaluate the effectiveness of a new medicine through clinical trials, they are using statistical methods. Even the weather forecast you check on your phone is a product of complex statistical models analyzing historical data. Understanding the basics of statistics gives you a special lens to see the world, allowing you to critically evaluate claims. To truly begin our journey into statistics, we must first understand its two major branches. Think of them as two different but related jobs. The first is descriptive statistics. The second is inferential statistics. They work together, but they answer very different types of questions about our data. Imagine you have collected the final exam scores of every single student in one specific classroom. Descriptive statistics is all about summarizing and organizing this data. It helps you easily understand what's in front of you right now. Descriptive statistics uses simple tools to paint a clear picture. Average score, highest and lowest scores, the range, most common score, the mode. These are descriptive measures. They state facts, not guesses. Now, the other side of the coin, inferential statistics. Think of it like being a detective. It uses a small group's data to make educated guesses about a larger group. If you only had one classroom's scores, you might estimate the whole school's average from that classroom average. That's an inference, sample to population. Inferential stats is powerful because we can rarely collect data from everyone or everything. When we have a set of data, the first thing we often want to know is, what is a typical value? This is where measures of central tendency come in. The three most common measures are the mean, the median, and the mode. They are like different ways of pointing to the heart of your dataset, and each one tells a slightly different story. Understanding all three gives you a much more complete picture than relying on just one. First up is the mean, which you probably already know as the average. It is the most common measure of central tendency. To calculate the mean, you simply add up all the values in your dataset and then divide by the number of values you have. For example, if we have the test scores 70, 80, 90, 90, and 100, we add them all up to get 430. Since there are 5 scores, we divide 430 by 5, which gives us a mean of 86. The mean is great because it uses every single data point in its calculation, but it has one major weakness. Next, we have the median. The median is the true middle value in a dataset arranged from smallest to largest. Let's use our scores again, 70, 80, 90, 90, 100. Since they are in order, we find the middle one. In this set of 5 numbers, the middle value is the third one, which is 90. So the median is 90. What if we have an even number of values like 70, 80, 90, 100? In that case, there is no single middle value. So we take the two middle values, 80 and 90, add them together and divide by 2 to get 85. The median's superpower is that it is not affected by extreme outliers. Finally, there is the mode. The mode is simply the value that appears most frequently in the dataset. In our example set, the number 90 appears twice, while all others appear once. Therefore, the mode is 90. A dataset can have one mode, more than one mode, or no mode at all if every value appears only once. The mode is particularly useful for categorical data, like finding the most popular color of a car sold or the most common t-shirt size. Now let's see how easy it is to calculate them with Python. Python is the preferred language for data science and has powerful libraries. For these calculations, we will use NumPy. Let's imagine we have a list of salaries for a startup team: 50, 60, 65, 70, 75, 80, 80, 90, 150. First, let's calculate the mean. In Python, we can use NumPy's built-in mean function. Notice our outlier salary of 150 will significantly pull the mean upwards, making it seem higher than most earn. Next, let's find the median salary. The median gives us a better idea of typical salary because it isn't affected by that high earner. In Python, we can use NumPy's median function. This automatically sorts the data and finds the middle value. As you'll see, the median salary is lower than the mean, more accurately reflecting the middle pay scale. Finally, let's find the mode. In our dataset, 80,000 appears twice, while others appear once. Therefore, 80 is the mode. Knowing the central tendency of our data is a great start, but it doesn't tell the whole story. Imagine two different classrooms. In both, the average exam score is exactly 75%. In the first classroom, all students scored between 70 and 80%. But in the second, scores are all over the place. Even though the average is the same, the experience in these classrooms is totally different. This is where measures of dispersion, or spread, come in handy. They tell us how spread out our data points are. The first important measure is called variance. It measures the average squared difference of each data point from the mean. First, calculate the mean. Then measure each number's distance from the mean, some above, some below. We square these differences. We square to get rid of negative signs and give more weight to points farther away. Finally, we calculate the average of all squared differences. Small variance means tight clustering. Large variance means wide scatter. While variance gives us precise spread measurement, its units are strange. If measuring percentages, variance would be in percent squared. This is where standard deviation comes to the rescue. It's simply the square root of variance, bringing us back to original units. Standard deviation is much more intuitive. It gives you a standard way of knowing what is normal and what is extreme. For normal distributions, about 68% of data lies within one standard deviation of the mean, 95% within two. If mean score is 75% with standard deviation of 5, most students scored between 70 and 80%. Python makes calculating dispersion measures straightforward. We can use NumPy's var and std functions with single lines of code. Classroom A has standard deviation of about 1.41, while Classroom B has 14.14, 10 times larger. This single number summarizes the consistency difference, helping teachers know if uniform methods work or personalized approaches are needed. This is the power of using measures of dispersion to look beyond the average and understand the full story of your data. At its heart, a lot of data science is about dealing with uncertainty. We can't know for sure if a customer will click on an ad or if it will rain tomorrow. This is where probability comes in. Probability is the branch of mathematics that deals with likelihood of events occurring. It gives us a way to measure and reason about chance. The value of a probability is always between 0 and 1. 0 means impossible, 1 means certain. Everything between represents sliding likelihood. Let's use a simple example. Rolling a standard 6-sided die. The set of all possible outcomes is 1, 2, 3, 4, 5, 6. What is the probability of rolling a 4? There's only one outcome that is a 4, and 6 possible outcomes total. So the probability is 1 divided by 6, about 0.167. What about rolling an even number? The even numbers are 2, 4, 6. That's 3 favorable outcomes, so probability is 3 divided by 6, 50%. This basic idea is the foundation for how data scientists think about uncertainty. For example, a company analyzes historical data and finds that out of 1,000 visitors, 30 made a purchase. Favorable outcomes, 30. Total visitors, 1,000. So probability is 30 divided by 1,000, 3%. This simple probability becomes powerful information for business forecasting and decision-making. This concept extends to more complex scenarios. Data scientists use probability distributions to model real-world events. For instance, the normal distribution can model people's heights, measurement errors. Other distributions can model customers arriving at a store or time between phone calls at a call center. By understanding probability of events, data scientists build models that predict outcomes, simulate scenarios, and quantify risk. Now we arrive at one of the most powerful tools in statistics: hypothesis testing. This is a core part of inferential statistics. It provides a formal process for making decisions based on data. It's like being a scientist in a lab. You start with a hypothesis, an idea or claim you want to test. Then collect data and use statistical tests to decide whether your data provides enough evidence to support that hypothesis. It's a structured, data-backed guess. Let's imagine a pharmaceutical company develops a new drug to lower blood pressure. Their hypothesis, the alternative hypothesis, is that the new drug is effective at lowering blood pressure. The opposite idea, that the drug has no effect, is called the null hypothesis, the default assumption. The goal is to gather enough evidence to reject the null hypothesis. So the company conducts a clinical trial. They give the new drug to the treatment group and a placebo to the control group. After a few weeks, they measure blood pressure of all patients. Now they have the data. The crucial question is the average blood pressure reduction in the drug group significantly larger than in the placebo group? Or could the difference just be due to random chance and natural variation among people? This is the question that hypothesis testing answers for us. The process involves calculating a p-value. The p-value is the probability of observing your data or something more extreme. If the null hypothesis were actually true, in our example, it's the probability of seeing such a large difference if the drug had no effect. A small p-value, typically less than 0.05, suggests our result is very unlikely due to random chance alone. This gives us strong evidence to reject the null hypothesis and conclude that our drug likely has a real effect. This is just a teaser, but it's a critical concept for making real-world decisions with data. Now let's see how all these concepts come together in a real-world A/B testing story. We'll use descriptive stats, probability, and hypothesis testing together. Imagine you work for an e-commerce website. The marketing team has designed a new Buy Now button. They believe its bright green color will attract more clicks than the current blue button. But they don't want to just switch and hope for the best. They want to use data to prove it's a better choice. This is a perfect setup for an A/B test. First, we use principles of inferential statistics. We can't show the button to every potential customer, so we take a sample. The website randomly shows 50% of visitors each version. Version A gets the blue button, version B gets the green button. Over a week, 10,000 people see each version. The website records how many people in each group click the button. This is our data collection phase. Now descriptive statistics come into play. Out of 10,000 visitors who saw the blue button, 1,000 clicked it. The click-through rate is 1,000 divided by 10,000 or 10%. For the green button, 1,150 out of 10,000 clicked it. Its rate is 11.5%. Descriptively, the green button performed better. 11.5% is clearly higher than 10%. But the critical question is this difference statistically significant, or could it just be random luck? This is where we use hypothesis testing. Our null hypothesis is no real difference in click-through rates. The alternative is that the green button's rate is higher. We would run a statistical test like a chi-squared test on our results. This test would give us a p-value. If the p-value is very small, say 0.01, there's only a 1% probability we'd see this difference by chance. This low probability gives us confidence to reject the null hypothesis and declare the green button the winner. We have used statistics to make a data-driven decision that could increase sales for the entire company. This is statistics in action. Today we've journeyed through the fundamental concepts that power modern data science. From descriptive and inferential statistics, to measures of central tendency and dispersion, to probability and hypothesis testing. We've seen how these concepts work together in real-world scenarios like A/B testing. These statistical foundations are your gateway to understanding the language of data science. With these tools, you can start asking intelligent questions about data and making informed decisions. Tomorrow, in Day 8, we'll dive deeper into advanced statistical concepts and machine learning foundations. If you found this helpful, please subscribe to continue your data science journey with us. Practice these concepts with your own datasets, and remember, every expert was once a beginner. Leave a comment below with your questions or share what you learned today. We're building something amazing together, a complete data science education in just 30 days. You're already 7 days into becoming a data scientist. Keep going. The best is yet to come. Thank you for learning with us today. See you tomorrow for Day 8.